Sorry about interrupting.
No, that's
No,
fine.
no, it was great. I'm recording now.
Okay, awesome. Thank you. Yeah, no, it's good. It gives my computer a chance to go back to being able to let me scroll. Need to figure out why it does that. Okay, so this function just has a very simple main. It just calls this function called calling function, which I called it that because I just wanted you to have an example of a function that calls other functions for when we look at the output from the profiling. Oh wait, actually, I should take a step back. So I think we've alluded to profiling a bit in the discussion we were just having and before, but let me just like talk a tiny bit about like what it is and why you would want to do it. So yeah, Matthew was talking about like kind of how there are different ways that you might want to measure like, you know, how fast different things are. And so profiling is a good way to do that. It's true that in general, people tend to profile their code once and just like take those times as gospel. It is often worth kind of repeating it a few times because there's variation. Although usually when you're profiling, the results that you get are like dramatic enough that like the error doesn't matter a ton. So yeah, profiling is a really great way to figure out what parts of your code are slow because often they're not the parts that you expect. And you can't actually speed your code up that much by making the parts that aren't taking a long time faster. You can only get a good speed up by actually speeding up the slow parts. And so profiling will tell you which parts those are. Okay, the questions about the general concept of what profiling is or why you might want to do it. And let me know if there are questions in chat because I can't see it. Okay, great. Okay, so main just calls this function called calling function, which is only here to have an example for you to look at of what it looks like when a function calls another. And so calling function calls two different functions, long function and short function. And so long function is just a function that has a for loop over a very large number of iterations in it. And short function is the same, except it only does 10 iterations. And here, again, just to like give you more interesting example to look at, we're going to call short function 10 times. So you can see what it looks like when different things are called a different number of times. So long function is the slow part of this code. And so we should expect to see that reflected in our profiling results. Okay, so normally we would compile this with our compiler and then the name of the program. If we want to be able to profile it, we need to add an extra flag, and that flag is -gp. And that tells the compiler to kind of put some additional infrastructure in the compiled code to keep track of how often we're calling each function and kind of what percentage of our time we're spending in each function. I should mention, the way profiling works depends on the language that you're using. In an interpreted language like Python, you can get much better information from profiling than you can in a compiled language. Because an interpreter like Python's has can kind of like do a bunch of like behind the scenes work to like keep track of stuff. Whereas G++ can't do that as easily. So G++ is basically just like watching like, the current instruction pointer and like checking every few seconds or few milliseconds probably where it is and like getting kind of a statistical picture of like, okay, on average, most of the time I check, like this is the part of the code that we're in. But there are limitations that there wouldn't be if it was an interpreted language. Okay, so yeah, we add the -gp flag to be able to profile and compile it. Oh, what? Wait. Oh, sorry, it's PG, not GP. There we go. Okay, so now our code is set up to be profiled. So the next step is we run it. And this creates a file called gmon.out that has some information about like where the code spent its time. So then to convert that into something that's actually informative about like what parts of this code are actually taking a long time, we use the program gprof. That's just kind of the best option that there is right now for profiling C++ code. So we do gprof and we do the name of the file. And if we were doing something fancy with like, if we'd saved the profiling information into a file other than gmon.out, we would need to tell gprof where it was. But since we're using the default of it being in gmon.out, we don't need to worry about that. So we can say gprof a.out, and it's going to spit out a bunch of information. So I'm just going to make my terminal bigger so that we can see it all. And so if we scroll up to the very top, the first thing it tells us is this kind of summary. It's called the flat profile, about how much time this program spent running and where that time was spent. So it spent 101.38, probably milliseconds is the unit there. I should have checked. Oh, no, that's the percentage of the time. Oh, I spent 101% of the time in long function. Like I said, there's some error here because of the way the sampling works. But yeah, okay, so long function is basically like where all of the time in this program was spent, is what that is telling us.
So I don't think it's just error. I think it's it has to do with the amount of time actually spent in the program versus shifting away to the system. And if it's left in that area while it's actually doing system stuff, it looks like that still counts toward the time and will skew numbers a little bit.
Ah, okay, thank you. That makes sense. Cool, okay, and so it's gonna tell us also how many calls to that function there were. So long function got called once, because we just called it once from calling function. Whereas we can see short function got called 10 times, because we put it in that loop that iterated 10 times and called it once from each time through that loop. We can see the total amount of time it spent on average per call. And difference between self and total, I always have to look up, but hopefully there is a description right here of what they all are. Okay, right, so total includes if there were other functions that long function had called and they took time, that would also be included in total. So you can see calling function has 202.76 in its total because it called long function. A long function took that amount of time. Whereas you look at the self for calling function, it's 0. Because basically all of the time that this program spent running descendants of calling function was spent in long function, not in the actual body of calling function. Because just to remind ourselves, we look at the body of calling function, it is very minimal aside from the fact that it calls long function. Yep, and then there's also some like kind of stuff that happens behind the scenes that will show up here as well. Okay, questions about this part of the output? Does everyone understand what all these numbers mean?
I've got a question.
Mm-hmm.
How can the time be more than like 100%?
Yeah, good question. So that's that thing that Charles was talking about where gprof, I guess, maybe Charles can explain this better, but tries to subtract out time that is spent on system stuff that isn't part of your code. And
yeah, so if you run time on something, so if you run something with the time command before it, it'll divide up the time for you. So I don't know if you want to do that quickly, Emily. If you
yeah, sure.
If you run the same command you did before, but with the time command in front of it, you'll see that it shows you how much time went by in real time, how much time went by in user time, so as in in the code you're running, and how much time went by in system time. And you see that system time, it depends on what else the system is doing, right? For how much time is in system time. And my understanding about what's going on there is that the system time is used in the numerator but not the denominator. Like, so it knows it only uses the real time in the denominator, but it can't subtract out the system time as it's doing all of its checks for where is it as easily. And so it stays in the numerator. As long as your system time is super low, that puts an upper bound on how much the numbers can get messed up. And it's usually at most about 101% sort of deal. Unless you're doing something else big in the background and whatever, that's using a bunch of cores. And, yeah.
And to be fair, I am running Zoom in the background, so that could be part of
Oh
this.
wait, maybe if you turn that off, you'll get better results. Oh wait, no.
Yeah, good question. Are there more questions about these numbers? Okay, so the other part of this output is this call graph, which is kind of like trying to break down like what called what and how. And this is like honestly a little bit hard to read, but basically what it's trying to show is, so main called calling function, and calling function called long function, calling function called short function here. We can see like the entire stack here, and it's basically trying to show us like how many calls there were to each and like how much time it spent each of them. This 10 out of 10 number here is saying that short function was called 10 times in total. That's the second 10. And that 10 of those came from calling function. So like if short function were being called in multiple places, we would see like different numerator versus denominator here. And there's more explanatory text on that here.
Do you want to say a few words about why we would care about the different versions of total time versus whatever is called time in function, and this whole breakdown? I mean, the key idea being that when you're going through and optimizing, if you can reduce calls to something, that you subtract off total time, right? So total time is the number you want to look at to say, hey, if I prevent this from being called, what happens? Whereas the time in function, I forget what they called it here, is most useful for, do you want to spend your time in that function optimizing things versus things below it?
Mm-hmm. Yeah, exactly. Right. So that's what this self versus children thing is. So, you know, technically everything is coming from main, but main is spending no time on itself and all of its time on its children. So if you want to optimize this, you probably want to be like doing your optimization within the children of main. Okay, so like I said, this is not a very easy to read format. So it's really helpful to visualize the output of this. Unfortunately, there are not as many good visualizers for gprof output as I was hoping there would be. There used to be one called kcachegrind that worked really well, but when I was preparing for this demo, I couldn't get it to actually display the output. So the best thing I have to recommend right now is this Python tool called gprof to dot, which basically you run it through this. And oh, I'm gonna just paste the link to this in the chat so that you all have it. And yeah, this is just a simple Python program that will create a picture of your gprof output that you can then look at. So there are pretty good installation instructions in here that you can use to get it running on your computer. I've already done that. And so it's also got pretty good instructions for how to use it with different types of profiling software. And so for gprof, it recommends just like directly piping the output of gprof into a call to gprof to dot. So we can do that if we want to visualize our gprof results. So I'm just gonna grab that back. Yeah, okay, so here we're calling gprof to dot on a dot out. Sorry, we're calling gprof on a dot out. We're sending the results of that into gprof to dot. And then gprof to dot is doing this thing where it's outputting instructions for how to make a picture in this format, this program called dot understands. Dot is a really common utility for representing kind of like graphs where you've got nodes and edges. So gprof to dot is basically doing its thing, and then we're sending it into dot to make the actual picture. You don't need to worry a ton about that. Basically, you can just copy this command off of gprof's or gprof to dot's GitHub page, but just a little context on why this does what it does. So if we run this, it'll work. And now there's going to be a file called output.png. So I'm just going to open that up and we can see what it looks like. Okay, and it's pretty simple because this is a very simple program. But you can see it's not even bothering to show us short function because it spent so little time in short function. But it's showing that main called calling function, which called long function. And saying, you know, 100% of the time is spent in main and its child processes. And of those, 100% of time is spent in calling function and its child processes. And of the 100% of it is spent in long function. Does that make sense? Okay, so like I said, this is a very simple example. So I just want to quickly show you what this would look like on like an actual piece of code that you might want to optimize. So just as an example, let's go into the empirical examples directory. I'm going to go into evolve because, you know, a lot of us have been dealing with stuff vaguely related to evolution. And so if we just choose the first thing here, Avita GP-evo, which you don't need to worry a ton about what it does. It's a program that evolves some Avita style genomes to do, I forget what they're even trying to evolve to do. They're probably trying to evolve to solve simple programming problems.
Is square numbers.
What?
Is square.
Oh, awesome. Thank you, Anya.
I'm looking at it a lot, so.
Okay, so just to get the correct compiler command, I'm gonna run make, oh, whoops, sorry, I was testing this out before. RM Avita GP though. Okay, I'm gonna just stop that and grab this command just because that's easier than remembering what the compilation command is myself. And I'm gonna copy that and paste it. And I'm gonna just add that -pg flag so that it will do the profiling. And it's gonna compile. And then I'm gonna run it. And it goes through some actual evolution, so it takes a bit. These are all generations. I think that last number is fitness. You think this might be like the number of correct squares. Yeah, and then here at the end it outputs like one of the programs that it evolved. So you can see it's like evolving actual assembly code. It's kind of cool. You can take a look at it later if you want. But the key for now is just that it did indeed generate this gmon.out. So just like before, we can do this gprof and then send it into gprof to dot. We could also just run gprof on it, but I'm gonna skip that step because with longer, more complex programs, it's kind of even less intelligible to look at just the gprof output. Yeah, and it's giving us this warning about cycle 1 as a whole entry missing. I think basically that means it's somehow failing to like put main into the image for this graph. I'm not totally sure why, but it's okay. It's still interpretable.
It might have something to do with, I forget if we look at the code, I might have used a macro to create main.
That would do it.
I don't know if it has anything to do with it.
Yeah, I'll just pull up the code quickly because it's probably good to see it if I'm using it as an example anyway.
I know I was playing with some ideas like that, you know, the macro sets a whole bunch up. I don't remember if this example.
Yeah, it looks like it's got a normal main.
Yeah.
Yeah, so this may be kind of familiar to some people in that it looks kind of similar to that demo evolving thing that you wrote during the tutorials in the first week. Setting population, doing some mutations, doing some selection, evolving some code. Okay, so, right. We just generated the graph of what the profiling looks like. And that's going to be in evolve, and it's going to be output.png. Wait, it was just here. Where did it go? Okay, that's weird. Yeah, it's right there. Why is it not showing up in my file browser? Okay, there it is. Okay, and so you can see this is a much larger image because this is a more complex program. Fortunately, it's at high resolution, so we can just zoom in on it. And so, yeah, like I said, it's missing main for some reason. The way you can interpret this is basically as if there was a main on top that had called all of these things. So everything that's kind of parallel to each other is like at the same level of like depth into the stack. So you can also see from this view that it's actually helpfully color coding stuff for us by how long it takes. So if we zoom in a little more so you can actually see, you can see that everything that's in blue is taking, maybe like a substantial amount of time, but far less time than this green stuff here. So we can see that 52% of the time spent on this program is spent in this calc fitness ID function. Which for those of you who are familiar with evolutionary algorithms, this will make a lot of sense because normally the slow step is calculating the fitness. Because basically what that function has to do is run the actual source code of the programs like a bunch of different times on different test cases to see if it works. And so that takes a very long time relative to just kind of like having to look through the population and the rest of the code. And moreover, we can see that basically all of that time is spent in this subfunction here, which I'm just showing you this because I want you to know what it looks like and not be scared when you see it. This is what a lambda function looks like in this output. This is one of the downsides to using lambdas. Because they're not named, your compiler can't give you like nice, like, oh, it's this function information. Instead, it is saying, I don't know what this function is. It's a lambda that was created in this scope with like these arguments, and you have to figure out the rest. Fortunately, in this case, it's not too hard because basically you set the fitness function in this context with a lambda function. So obviously it's going to be that lambda function that this is spending time on. Yeah, so I'm not gonna like walk through this whole thing because it's very large. But yeah, you can see that this is pretty much mapping out all of the calls that are happening in this program that take any substantial amount of time. You'll notice that, yeah, a lot of these function names get kind of long because they have like the entire scope and the entire like template signature baked into them. So again, don't be intimidated when you see that. It's just trying to give you all the information you could possibly want, which is often more information than you want, but it's there in case you need it. Any questions about this?
I have a question. So I get an error when I run the when I try to compile with PG option.
Oh, interesting.
It tells me that there is. I posted the error in the group chat.
Oh yeah. Okay, I see it. Oh, you're using Clang.
Yeah.
Okay, the profiling flag for Clang might be different. I would need to double check.
Okay.
I will look that up after this presentation and I'll get back to you on that.
Okay, thank you.
No problem. Any other questions?
I guess one question I have is, like, do you have any stories about like using profiling and like how you used it or like what decisions you made based on it?
Oh, good question. Honestly, that actually brings up a really good point, which is that I've been talking about time profiling. So profiling to figure out how long something takes. That's not necessarily the only thing you'd want to profile for, though. Profiling to see how much memory different things are taking is also very important. And that's something I've done a lot more of because I tend to do things where memory can get out of control because I'm like recording information about whole evolving populations. And honestly, I haven't found a memory profiler that I'm super happy with. Valgrind is like the best one out there, but it's a little unwieldy for actually figuring out like why different memory was used and when. But definitely I have like used Valgrind to figure out that like the amount of memory I was spending on something was like, I guess there were two cases. One I found where like, yes, like I was trying to store too much information. It was huge. And like I had to use a different data structure that didn't record all of that information. But there was another one where I thought I was doing that again, but I was actually wrong. I didn't need to be using that much memory. I just had a memory leak. And so being able to tell the difference between those two, I think is one of the most important things. And there's absolutely an equivalent with time for that, which is like, it's easy to like run something and have it take a long time and think, oh yeah, like, you know, that program's doing a lot. Of course it takes a long time. But then to look at it and find out, oh, actually, no, it was doing this whole thing that it didn't need to be doing and I could have gotten rid of that. It did not need to be taking that long. I think that's the biggest win I've had with time profiling.
So I'm happy to give lots of more concrete examples if you want.
Yeah, go for it.
Because the sorts of things that profiling has helped me debug so many things. You know, some stuff that was running correctly, as in it was giving the correct output. But for example, that I meant to pass something by reference, or rather I should have passed something by reference, but passed it by value. And I see, wow, why is this taking all of its time you know, copying vectors of doubles? I only create a bunch of those at the beginning and then just keep reusing them. Why should it be in the copy constructor of that? Oh, right. And then you see where it calls the copy constructor and you realize, oh, that should have been passed by reference instead. So that sort of error I frequently will catch using profiling, particularly on those spots where it actually matters, where the profiling lets me know that this is a time-sensitive area, and doing all the copying there is slowing things down. I've also had it do similar sorts of things, like one of the things that I did when I was first learning C++, to give an example from a long time ago, was I built my own string class, right? I wanted to understand how the standard library string worked. I was at that time, obviously, you know, primarily using C-style strings. And I wanted to see, could I wrap the whole thing myself? And I did, and I was learning all sorts of C++ from this. And I really liked the strings I built, and so I was using them for quite a bit after that. And one of the things that C++ allows you to easily do is allow for automatic conversions, right? And so, you know, of course, I had things like automatic conversions to standard library strings. So if ever I used my string somewhere that was expecting a standard library string, it did the conversion. And then I got overexcited with the conversions. And at one point, I was like, all right, well, if you're going to convert a string to an int, that'll just be a quick way of doing string length, right? Just, you know, if you want to pass a string, and I don't know, I mean, obviously it was a brief idea that I foolishly put in, terrible, terrible idea. And then later on, in code that was fully working, right, it turned out that there was this whole series of calls that I initially tried to start with an empty string, and which was a string of length 0 that got converted to numbers and then got converted back to a string later on of length 0. And there's this whole long chain in there that was taking way longer than it should have, but gave the correct answer because it had all these additional conversions in it that just happened to work correctly. And I found that out when I was profiling my code, and of course ripped out the implicit conversion, because what was I thinking? So yeah, there's an example of a real world, you know, found a bug because something was taking too long. But there's lots of examples like that where when you see where your code is taking all its time, you'll look at it and you'll go, that's so easy to fix.
Mm-hmm. Yeah, great example. Thank you. Are there more questions? Okay, if not, then I will turn it back over to Matthew.
Great. All right. So I guess I'm going to ask Santiago, do you want to go now or do you want me to go first? I guess I should go first. All right. So what I'm going to be talking to you about is kind of related to what Emily was talking about, but it's along the lines of how can you, instead of trying to go inside, once you've gone inside of your program and you've figured out, oh, what are the things that I should be fixing up that are using all of my compute time? How can I test and see whether or not the optimizations that I made actually have an effect, and whether I should keep them or kind of maybe go back to the more simple way of doing things based on whether they actually work. And so one way to approach this is to use timings of either the subsection that you optimized or your entire executable, both with and without the optimization, and then compare those timings, and then see if you can detect a difference between the timings from doing it way A versus doing way B. So I'm going to take over the screen share, and I think I'm in this meeting. Oh, is my Zoom? Okay. Oh, okay. I'm here now. I'm going to take over the screen share and share this desktop.
Hey, I can go. My Zoom just crashed, and
Oh.
I actually. It's fine.
I'll finish up my segment and then hand it over to you if that's okay. Okay. So the first tool that I really like for doing these kind of timings is this tool called QuickBench, which it's all online, all on your browser, and it's good for doing micro benchmarks. So if you have just little snippets of code that you want to measure, this is a great tool for that. It really makes it almost zero effort, but the downside is because you kind of have this limited text editor in here, if you want to benchmark bigger pieces of code, this probably isn't the way to go. But the way that QuickBench is set up is that it uses Google's benchmarking library under the hood. And so it takes Google's benchmarking state, whatever that is, by reference, and then it does a bunch of replicates of whatever you want to measure. And then you just, inside of the for loop, you can just do the, write the code that you want to measure the run length of. In this case, I'm benchmarking different clocks, clocks through stood chrono, clocks, old style C clocks, and then just calling stood time, which is like another old style C thing. And what I'm trying to measure is how long does it take to actually check the time? What's the computational cost of checking the time? And I have it wrapped inside of this benchmark do not optimize, which is a little helper magic function that Google's benchmarking library has that says, hey, optimizer, like this thing actually really needs to happen because it's what I'm trying to measure, so don't optimize it away. And you can just set up these little chunklets for all the different variants that you want to measure. And then you just go over here and click run benchmark, and it will take your code and send it to one of its servers and just do the measurements of each of the little sub code chunklets for you. And it will report the results back to you. And it's already run here, so I'm not going to run it again. But what the y-axis is compute time relative to a single no operation call. So you can kind of think of this as the number of CPU cycles that each of these little chunklets is taking. And what we can see here, the results, steady clock, system clock, and high resolution clock, these are all through stood chrono, all take about the same amount of time. The C style clock takes more time than these other 3 clocks. And then the fastest is this time-based clock, which basically just, my understanding is that it's a super coarse-grained clock which only updates every second. And so checking it, because it updates so infrequently, is pretty cheap. And so things to point out here, it's kind of opaque what kind of statistics that, if there are statistics, or whether this is maybe put together in kind of a kludgy way, but it will, you can kind of get a sense of whether a difference in timings is significant based on these little readouts you get when you mouse over one of these, where it'll tell you it's equivalent to something if there's no significant difference in the timings. And if there is a significant difference in the timings, it will report to you that difference. So if we mouse over this, we can see that all 3 of these are equivalent because this is being read as equivalent to that. And I don't know what statistical methods this is using under the hood, or whether it's doing real statistics or just like being like, 10% is what we'll call significant. But that's better than nothing, I guess. And it is doing replicate measurements here. So this is a very good option for just micro benchmarks when you just want to try out a few different options really quick and get a takeaway that you can use in your code. And you can also, the URL links that it generates are, they'll always resolve to the same benchmark. And so you can, if you do a benchmarking and you make a decision based on that benchmarking, you can actually just link to the quick bench in a comment in the code and say, I did it this way because of this benchmarking result. And then people going through the code later on can just pull up the benchmarking result really quick and see what you tried, and double check that.
And actually, so I wasn't aware of that feature. I love that. That's something that that being able to go back and look at the same one later, because also as your code changes, you're able to, like you could have gradual changes. You could realize you haven't benchmarked in a while. You do your new set of benchmarks, and
right.
You come back and you say, hey, has all of the changes I've made over time made that big of a difference also, and compared to the old version. I love that. I feel like I need to use more of this. I have
you
not
can,
used the system.
you can pull up your old benchmark and then modify that based on your new stuff, and just not have to rewrite the whole thing, which is another great option here. And in terms of, so the downside is this is just one C++ file, and so there's limitations on what you can realistically, like how much code you can, and the complexity of things you can benchmark here. I think you can, it's set up so that you can put, if you want to include a header file, you can put like a URL to a header file as an include statement. So I think you just do like https github.com/your username/your project/path to your file.h, and it should, I think it can get individual header files. But if you've got a project where you've got header files depending on header files, it gets messy. And so you don't really want to go down probably that route of trying to like get all those URLs and paste them in here. But before I go on to kind of the other approach of like how you would accomplish this with a more complicated project on your own machine, I just want to stop and see if there's any questions or comments. All right, so the next part of the presentation is going to be a demo of just how to do some really simple timings on your own CPU, and how to do some really simple visualizations of those timings with confidence intervals, and how to actually do a statistical test to see whether your sample timings are different from each other. So I'm gonna put this over here and move the zoom out of the way and increase the font size. All right, so what we're going to be testing here is we're going to be making 2 executables that are actually under the hood secretly just the exact same thing. And then we're going to do a statistical test on the timings. And hopefully, if we do everything right, we'll be able to see that there isn't a significant difference between these executables. And I'm realizing that probably most of you didn't exist in the 90s, but when I think of things that are the same, I think of the Olsen twins. And so one executable is going to be named Mary Kate, and the other executable is going to be named Ashley. And we're going to be showing that Mary Kate and Ashley have the same timing characteristics. All right, so I'm gonna open olsen.cpp, and the first thing I'm gonna do is just paste in a bunch of headers that I'm gonna need, and grab those here. All right, paste. I'm gonna start a main function. And so when you do timings in C++, you kind of have 2 options. You can use the old style C libraries to get, for example, the number of seconds since epoch, and then do math that way. But kind of the fancy modern C++ thing to do is to use the stood chrono library, which it kind of takes a lot of the complications of measuring and representing time and moves it into the type system, and then really makes explicit, like you have to explicitly convert between seconds and minutes, and it helps prevent a lot of kind of the typical errors that people make when working with just time as raw values and trying to take care of all that themselves. So the first thing I'm going to do is I'm going to make a chrono time point, which is going to capture a moment in time, or like a time coordinate from before we start doing work. So it's going to be called before. And I'm just going to initialize it as a stood chrono steady clock now. And chrono has several different clocks you can use. Steady clock is one of them. There's also high resolution clock, and I think system clock. And if you want to be timing actual, I don't want to say physical time, but time in terms of how we think of it as people, you might have heard it referred to as wall time, like wall clock time. You want to be using the steady clock. And then we're going to go and do some work. And so all we're going to do is stood this thread. We're just going to sleep the thread for a certain number of seconds. So we're going to make some milliseconds from chrono. And we're going to choose a certain number of seconds. I'm going to do that in a second, and I just have to close this and close this. So in order to have interesting data, kind of when I was playing with this, I figured out that it will have more interesting data to analyze if there's some kind of variance in the timings that we take. And unfortunately, like there's inherent variability in whenever you do timings, but that variability isn't large enough for it to be noticed at kind of the granularity that we're working with. And so we're going to kind of draw an amount of time to sleep from a little bit of a random distribution, just so that we can introduce some noise into our measurements, so that like the visualizations and statistics that we do later will be interesting, instead of having everything be exactly like, for example, 100 or 1,000 milliseconds. So we're going to they're going to go sleep for a while. And so the Olsen twins are famous for having really fun sleepover parties. So we're just going to schedule a sleepover party. And then how we're drawing this random number really isn't important, but I'm just going to copy some code that I wrote. And basically what we're going to do is, I know that Mary Kate's favorite color is yellow, and I know that Ashley's favorite color is maroon. So we're just going to take that and then run that through a hash, and then basically generate a range of random numbers from those hashes, and then draw a random int from inside that range. So anyways, that's like a not important detail for this demo, but I thought you might appreciate knowing the inspiration here. All right, so we're just going to draw a random number and sleep for that amount of time. All right, so now we just have to compile this, and hopefully this will compile. So the first thing we're going to do, I don't want to do that. No. So I'm just going to save the first executable as Mary Kate, and I need to use C++17. What did I mess up? Stood chrono milliseconds. I'm gonna go back in there and see what I messed up. So, stood chrono milliseconds. Stood. Does anybody have any ideas of where my syntax error is?
In the before section, is there supposed to be a semicolon like online?
Oh, on this line?
Steady clock. Yeah.
I think so. I think this semicolon ends this line.
Well, within on line, what is now line 3 below you, now line 4 below you.
Oh, sorry. Yeah.
At the end of that.
Oh, that's it. That's it. Yep. Okay. Good point. Okay. We'll get rid of that. Okay. There we go. All right. So we're gonna. Okay. We just compiled Mary Kate. So now we're gonna compile Ashley. All right. So now we've got Mary Kate and Ashley, and what I'm gonna do is, so I'm just gonna run one of them. Oh, I didn't print the timing. Did I have that as part of the original file? Oh, I totally just forgot to put that in there. So I'm just gonna paste this print statement in there. So we took a timing, but we didn't print it. The joys of live coding. All right. So here, all I'm doing is I'm taking after minus before and telling stood chrono to represent it as milliseconds. And it's going to print out how many milliseconds elapsed. So now I need to recompile Ashley. Oh, and then I also forgot to take the, all right. I also forgot to take the actual timing at the end. So now I need to click my stopwatch to end the timing. So I'm gonna go put that in there. All right. So I started my stopwatch, I did some sleeping, and then I clicked the stopwatch close, and I'm gonna print out the elapsed time. Mary Kate, and I've got Ashley. All right. Yep. So you can see as kind of I do these timings that there's a little bit of variability going on. And so the question is, can we tell whether or not these are actually, like, if we were doing an optimization and we thought, oh, we did something clever with Ashley where Ashley is going to go faster than Mary Kate, can we actually tell if our optimization did anything? And so on the enrichment site, I put up a little bash script that I use to just do a bunch of runs and stream that all into a CSV. But in the interest of time, so that Santiago has some time to present, I'm going to omit actually doing that. And I'm just going to paste in the data that I've pre-generated from this. So you'll have to trust me a little bit on that. So I'm going to open Olson timings.csv. And we can see what I have here. I have 3 columns. The first is just which algorithm I was running, whether it's Mary Kate or Ashley. The second is the replicate number, and I did 10 replicates of each algorithm. And then this is just the number of seconds elapsed. All right, so I've got my data. And the key thing here was doing replicates. We can't just take one timing as face value if we want to actually concretely make an assessment about whether there's a significant difference. We need to actually take multiple measurements in order to have statistical information. So the first tool I'm going to talk about is using this tool called Seaborn to really easily generate a bar plot with confidence intervals. So paste stuff in here. So what I'm doing is I'm importing, this is a Python script, I'm just importing some stuff. I'm reading the CSV, and then it's just as easy as calling Seaborn, hey, draw me a bar plot, and then saving the figure out to a file. And all this code is linked. I know I'm going pretty fast here, but all this code is on the enrichment page. And so now I can just plot. And this is because everything is broken, but I have my PNG. So I'm going to open up timings, move it over here. And so, oh, this is garbage background. But so there's some transparency here that's making it kind of hard to see what's going on just because of how this particular PNG viewer is. But what I want to draw your attention to is Seaborn put these little confidence intervals on our bar graphs. And so what it's saying is, hey, based on these 10 measurements that you took, I'm 95% sure that the actual mean timing that you'll get from either one of these is somewhere inside of this range. And so one kind of quick and easy way you can see if there's a statistically significant result is just to do bar plots like this. And if the 95% confidence intervals obviously don't overlap, then you can be pretty safe in assuming that there's a significant difference in the timings. So that's unfortunate that this is so ugly, but I'm going to persevere.
I think you can rerun it without transparency on and it'll look fine. Like if
Oh, that's actually good, yeah. I'll just do that. Good point. Right. So then the other thing that I'm going to talk you through very briefly is doing a statistical test to actually do a more formal assessment of whether 2 timings differ. But the first thing I'm going to do is, okay, this is what it looks like with the background proper. So you can see that these these bars aren't identical, but that there isn't really a big difference. These 95% confidence intervals look like they are overlapping. All right, so the last thing I'm going to coach you through is doing a statistical test. And so I'm going to use another Python package, SciPy stats, to do this. And I'm going to use a test called a Kruskal-Wallis test, which is a non-parametric test, where basically you give it two sets of data, and it will look at kind of, my understanding is it looks at rankings and medians, and so it doesn't make assumptions about how your data is distributed, and it will tell you, hey, is my null hypothesis that these are from the same distribution where they would have the same mean, and if I were to do like rankings between them, the actual order of time rankings would not have a detectable signal.
Yeah, so if you rank all the, if you take all the results from two distributions and they were actually the same distribution, you expect the results to be interlaced, right? You know, from one to the other, not perfectly interlaced, but like mixed all together. But if you see that, you know, you get the results out and you get, you know, you have 100 points from A and 100 points from B, and all 100 points from A come before all 100 points from B, you can be pretty darn sure, that's an extreme case, you know, but you can be pretty darn sure that these are actually different distributions. And what Kruskal-Wallis will help you do is figure out how likely is it that if these were the same distribution, you could have gotten a result that was this extreme in difference, and related ideas to that.
Yep, that's exactly it. Yep. And then all that's going on in this part is a little bit of Python fanciness. That is just, we're taking our data frame and we're just saying, okay, give me the seconds for Mary Kate and the seconds for Ashley, and we're just going to compare those two sets of data and throw that into the stats.Kruskal function. So I'm going to run this, Python 3. I have to, this is, what did I call it? No, I'll just rename the CP star dot. I just hadn't, didn't have my CSV file named correctly. So I'm going to run this. And it's telling me a Kruskal-Wallis statistic, which isn't intelligible or interesting to most people unless you're really familiar with the Kruskal-Wallis test. But kind of the more useful thing that it's telling us is the p-value. And so the philosophy and interpretation of p-values could be a lecture in and of itself. But basically, it's kind of saying, like, what's the probability, if these were actually coming from the same distribution, that I would observe a effect, I would observe a effect of one having timings that are generally faster than the other as extreme or more extreme. And so this p-value is 0.11, or you can also say it as 11%. And so 11% of the time, I would expect just by chance to see something this extreme. And so usually the cutoff traditionally is 0.05. And so this doesn't meet that threshold of actually showing evidence that these distributions are different. And so we weren't able to statistically differentiate between Mary Kate and Ashley. All right, I'm gonna pass it over to Santiago. Unfortunately, we ended up with a bit of a time crunch at the end. We could also, what do we have scheduled for next week? We could also move Santiago to kind of the beginning of next week's enrichment. I don't know, what do the mentors think would be?
What do you remember what our plan is for next week? I don't have that offhand.
I'm gonna look it up. Enrichment. Talking about professional web presence.
Yeah, whatever the others think. We could also have Santiago make a little video of it.
Oh yeah, let's send that around.
Yeah, I'm fine with either, actually. Both work.
Okay.
Yeah, because we shouldn't go past 4, so, and I don't want to.
Yeah. Yep. We'll plan on doing that then.
Oh.
Maybe we can have Santiago kind of talk about like the general tools that he was planning on covering, just so you know that they exist in the time that we do have.
Yeah, so that's a great idea, actually. I was gonna talk about, so Emily talked about time profiling. I was gonna talk about memory profiling. In particular, is how to use Valgrind or Valgrind to profile memory, and also check for memory leaks in case you're not using empirical pointers. So there's different things you can do with it. Valgrind is actually a utility that holds other utilities in it. So there's different things you can do with it. You can check for memory leaks. You can check for like out of bounds accesses to arrays and vectors. You can also graph for example, the heap. So basically, hot memory you're using, and see all the allocations and frees you've done. I can go into more detail next during the video for that, because it's actually really neat how you can just visualize the memory your program is using at any point in time. And I was also kind of gonna talk about some of the failures or shortcomings that the Valgrind has. For example, when using static variables or memory in the stack instead of the heap. But yeah, there's if you look it up, there's a lot of tools, and you can keep adding more tools to Valgrind. There's also the chance to not use any tool at all. That gives you a stack trace if there's like an error, like a seg fault or something going on. So it's very versatile. It's also really not user friendly, which is kind of why it's important to go over it in detail, because it's kind of really weird to use, and there's a lot of non-intuitive ways in which you can fail to actually know what's going on. Like there's really weird, sometimes even the limitations sometimes actually happen even though they shouldn't be happening, and there's ways to overcome that, but it's not very intuitive. Like I'll go into more detail that next time. I also have to install it, because you can install it and get some of the tools missing, which happened to me. I was gonna run like an experimental tool that actually didn't come with my version of my distribution. So it's kind of how to set up. I was just gonna talk about how to set up Valgrind, and yeah, those tools you can use.
Cool. Yeah, I know a lot of people use it to check for like memory leaks is like a really common thing that people use it for.
It's really good at that. It's because it also I think you can get it to tell you like where the leak is coming from too, not just or at least where the leak should happened.
Right.
Which is not.
Or you can at least you can see the data type that's filling up all your memory and kind of guess that.
Yep. Yeah. And that combined with the graph, you can also see memory usage and see if at any point in time you have like a spike for some reason, like if you have a weird copy instead of a move. But yeah.
Cool. All right, so then I guess everybody keep your eyes peeled. We'll post an update with some of that content on the enrichment Slack. All right.
It sounds great. Thanks, everyone. And I really appreciate all of you pulling these together. This was some really good stuff. I learned a good bit too, so yeah.
All right, see you all next time.